Okay.
I'm recording from now. Okay. I've opened tinkercad, then I opened a new project, and now I have just imported a small breadboard in my workspace. Now I want to set up all the power connections, power supply first. So as Sir has showed us, I'm going to use an Arduino Uno R3 as the power supply. I'm sorry because I have a poor internet connection. It's really bad. Okay, so I have the Arduino. Now I need a resistor. Do you know why we use this resistor?
No.
Okay, this resistor is
I think
actually,
pass.
okay, this resistor will be in parallel with our total circuit. We know that in a parallel circuit, the components which are in parallel, they have the same voltage in their both terminals, same voltage difference in their terminals, but the same amount of current do not pass through them, right? So we use this resistor in parallel with our total circuit so that the extra current goes through this resistor and not the circuit, not the total circuit. If we don't add this resistor, more current is going to pass from our total circuit and it's going to burn our ICs. You may have noticed that if we don't use this resistor, our ICs are going to get burned because they have a limited amount of current tolerance. So let me just I'm going to do it as slowly as possible. This is the 5-volt wire, right? Let's make it red. JJ, you had made a mistake in this part, remember? You had connected this resistor in the other node. Okay, let me just move it a little bit. No, it was a mistake. I'm just going to delete this wire. Okay. Now, in this node, we will have 5 volt, and in this node, we will have 0 volts. So this is our ground. This is our VCC. So in our breadboard, we can see that we have a dedicated lines. We have 4 dedicated lines, 2 for the 5 volt and 2 for ground. So let's just short them. Let's make it red. And again, let's make this one red too. And this will be our ground, right? Ground is black, so let's make it black. Have you understand up to this part? Have you understood up to this part? Any problem in here? These wires, this wire and this resistor may seem like they're overlapping, but they're not. These act like real physical components. Like this goes over this resistor. But anyway, we have our power supply ready. This will be our power supply. And now what do we need? We need to make this whole circuit, right? So for a flip-flop circuit, we're gonna need a clock first. How can we make or simulate the clock? We can use a function generator. Okay, I'm just gonna keep it in here. Let me get the ICs first. So from here we can see that we have a XOR gate and a D flip-flop. Let me get the D flip-flop. D flip-flop. Be careful while connecting these ICs. You have to make sure that these perfectly fit on these small dots. D flip-flop and an XOR gate. Here's our XOR gate. Okay. I'm gonna minimize it and keep this in the side. Okay, so that we can see this while we're making the circuit. It's small enough. Let's just put it in here. Okay, so let's look at the wiring. T is our input, right? So how are we gonna simulate our input? We're gonna take a slider switch. We're gonna take the slide switch. Wait a second. Where's the input? Input one is. We can get in here. The left side is gonna be connected to 5 volts, which is equivalent to 1, and the right side is gonna be connected to ground, which is 0 volts, and it's equivalent to 0. Okay, and the middle line is our input line. That's connected to input 1A. Okay, is this the input? Let's give it a color, turquoise. We haven't done one important thing. I have to connect these ICs to the ground and VCC. This is power, right? It's connected to power. This will be red. This is ground, so it will be connected in here. Black. This is also power. It's connected in here. Make it red. This has to be ground. You see, in tinkercad we don't need to remember the pin names or the pin numbers of the IC. If I just hover the mouse over these pins, I can see the names instantly. Okay, so our ICs are now connected. This is okay, so this one is this input of the XOR gate, and the other input is going to come from the QT side from the D flip-flop. We have two D flip-flops in this IC. Let's take the output of the first one, output 1. So okay, so this is output 1, this is input 1B. Let's just connect them. This is inverted output 1. Okay, they're connected now. This portion is done. Now we have to connect the D with the output of the input of the D flip-flop to the output of the XOR gate. So these two are connected. This will be my output, right? This is reset 1. This is input 1. Okay, we've connected. It doesn't look good. We have gone through the lectures, right? Sir has shown us reset, preset, and clear. So preset and clear have other names. Just let me check. One is called reset, and let me check. I totally forgot what the other names are. Reset and clear. Okay, they are just known as set and reset. Preset and clear are known as set and reset. We know that reset and set, or preset and clear, they are active low inputs, right? So if they're low, if they're both connected to the low voltage, they'll be activated. So to deactivate them, we have to connect them to the high voltage node. If we don't connect them to the high voltage node, they will stay activated and they're going to interfere with the final output of our circuit. Where's the set? Please do tell me if you don't understand anything, if I am unable to make you understand anything. Okay, so these are connected. And now output is connected to the input. So we have connected these two, and this, and reset and clear. Now we have to make this clock. Where's the clock? Input 1, reset, input 1. This is clock. Let's make this orange. This is going to be the clock. Let's make this 1 hertz. You can keep it 1000 hertz, but it will be easier for us to understand what's happening in the graph. We can understand the oscilloscope output easily if we just make it 1. This is the ground. It's connected to the ground. Let's make it black. Okay. Now our circuit is actually ready, but we need two oscilloscopes to see the input and the output. Not the input and the output, actually, the clock pulse and the output. So let's take the oscilloscopes. This is our first oscilloscope. This is gonna show us the clock pulse. This is clock, right? Let's connect this right here. Connected. Let's make it black. And we're gonna need another oscilloscope to see the output wave shape. Input clock set, output 1. Okay, as we have used the first D flip-flop of this IC, we're gonna use the first output. Sorry, the wires are not straight. We can make them straight later. But I think everyone can understand what I'm trying to do. Okay, so our circuit is now ready. If the slider is in the left side, I'm sharing the screen, right? Okay, the slider is in the left side, it's gonna simulate 1 as digital input. And if the slider is in right side, it's gonna simulate 0. Who's texting? Are you guys texting? Yes, good, as I'm not texting. Okay, let me just start the simulation. Bismillah. I hope I haven't made any mistakes here. Bismillah. Okay. Oh, I haven't. We can see the output properly because I haven't synchronized their scales. Let me just fix it. Times per division will be 500. Because if we keep 100, we're gonna see a tiny limit of this big graph. We need to see more, right? We need to see the squares. Bismillah, let me start the simulation. Okay. What was this? This is my output. This is my input. What's wrong? It should be. This is my input and this is my output. I've made this 0. As I made it 0, it's holding the previous value. This is a T flip-flop, right? So if I make it 1, it's gonna toggle. T stands for toggle. This is the input clock pulse, this is the output. So how is it toggling? This range is small, but these are too wide, right? Why is it like this? Because we know that these are edge-triggered flip-flops. So our flip-flop is gonna work when it comes across an edge. Right here we can see an edge. So this value is going from 0 to 1. After all these spaces, we're gonna find another edge. Here, it found another edge and it just toggled. It went down. Right? Hello, JJ? JJ, can you hear me? Hello.
I can hear you.
Okay. Did you understand everything?
I can hear you. The output, the results, I don't understand that part.
Okay, you don't understand the results. Okay, so
yes.
What does a T flip-flop do when it is connected to 1? It toggles, right? It means it goes from 0 to 1 and 1 to 0, 0 to 1. But here we can see that these clock pulses are really thin, but this output is fairly wide, right? So why is it like that? Shouldn't it toggle within this portion? But these flip-flops are actually edge-triggered flip-flops, right? So when let me look at this clock pulse. I can see this clock pulse here. In the clock pulse, at first, if the output is 1 at first, when I come across an edge, it will go down from 1 to 0, and then I see another edge, then it's gonna toggle. So the toggling actually happens right here and in here and in here. These are positive edges. The toggling only happens only when we come across a positive edge.
It means when you touch the edge of the input,
Yes,
it is shown on the output, the toggle value, the
yes,
toggle
yes.
output.
Yes,
Oh, okay.
that's why these are too wide. This width is actually the distance from one positive edge to another positive edge, right? One positive edge to another positive edge. We can see that one positive edge to another positive edge. So is it clear now? Hello.
Yes, it's clear. Yes.
Okay. Did you understand?
Yes, I understood. You said for the reset and the set.
Oh, for the reset and the set. Okay.
Yeah, you said they are active low, right? Inputs.
Yes. Active low. What does set and reset do? Do you know that? Okay, let me show you something. I'm gonna just Google a photo. So it's a latch, not latch. FF with preset and clear. Let me just show you a photo. Okay. Can you see the photo of the SR flip-flop?
Yes.
Okay. So without this preset and clear, we have a normal SR flip-flop without this preset and clear. What this preset and clear does is it forcefully makes the output 1 or 0 according to our needs. Okay. If I want to make this Q forcefully 0, I have to activate this one, this line. If I want to make at the same time, this one has to be deactivated. If I have to make this Q output 0, I have to activate this one, and at the same time, this one has to be deactivated. Preset and clear. Okay, so how do we normally activate a line? We put positive 5 voltage, right, to simulate 1, right? If I want to activate it, I have to put 1. But this preset and clear, they are active low inputs. They act in the opposite way. If I make this 0, this will be activated, and if I make this 1, this will be deactivated. Same goes for clear. So if these are activated, they're gonna interfere with the results, right? Like these are forcefully making the outputs something that we don't want. If this is activated, this will always remain 1. If this is activated, this will always remain 1. I'd like to add something. If preset and clear are activated at the same time, it's actually an invalid condition. We have seen an invalid condition in case of SR flip-flop, right? So this is also an invalid condition.
Yes.
Preset and if for any flip-flop, if I preset and clear 1.
You mean if you
Yes.
If you activate both of them at the same time.
Can you please repeat that? I didn't hear you.
I said, you mean if I activate both of them at the same time?
Yes.
It will bring an invalid input, output.
Yes, exactly. It's going to be an invalid output. So we don't need their interference in our circuit, right? We have to deactivate them. So as these are active low inputs, we have to make them high in order to deactivate them. That's why I have connected these with the 5 volt. If they were active high inputs, we have to make them 0. But no, these are active low inputs. So to deactivate them, we have to make them 1. And 1 is what? 1 is actually 5 volts in real life. So do you have any questions? Like anything about the circuit? Why this circuit burns? Anything?
Okay, why do the circuit burn?
Okay.
Like yesterday, my IC.
Yes, I have seen that. These ICs are made of like small BJTs or MOSFETs. BJTs and MOSFETs cannot take high current, like 5 volt supply. Maybe I'm giving 5 volt supply, but the current is like 20 ampere or 1 ampere. These are too high for these circuits. These are like tiny tiny, they have tiny wires, right? These are just going to burn if I pass more current through them. So in order to activate, in order to work, they need really, really small current, like in microampere range or milliampere range. If I supply more current, they're gonna just burn. Sometimes we see in our households, like maybe our lights have burned, fans have burned. Why does that happen? Because more current passes through them. They can take that current, so those wires just get burned, and it's a total mess. Do you
Yes.
wanna see how it burns? Let me just show you. I'm gonna disconnect this Arduino, and I'm gonna bring in a 9-volt battery. Power. These wires are already shorted, so I just have to connect this with here. I just did the exact same thing. I'm doing the exact same thing that I did with the Arduino.
Okay.
Okay, let's simulate it. Both the ICs burned. This device broke because of supply voltage is 8.99 volt, while permitted range is between minus 500 millivolt to 7 volt. Okay, so this is not going to work. In the
Yes,
same
yes.
way, you may see that sometimes you supplied only 5 volt, but still the ICs are burning. Why does that happen? Because although the voltage is right, the current is way above the permitted limit. Let me show you an example. We use this resistor so that the extra current passes through it. Let's just remove it and see what happens. Okay, so these are shorted. Okay, let me just remove them. I'm going to show you what happens when the current is too high. Let me just short these. This is ground. I'm not using any resistor or anything. I'm just giving direct 5-volt supply.
Okay.
Bismillah, let's start the simulation. Okay, for the Arduino, the current is actually limited by this Arduino. That was used for safety purposes. But I had used other batteries, like this 1.5 volt battery. I had used 3 of them. Arduino has a voltage regulator and current regulator too. This is the voltage regulator of the Arduino. I forgot the name of this IC. This one right here. But this one does all the work that just lessens our hassle. So you can use this Arduino without the resistor, but that was just for safety reasons. But sometimes more current passes through these ICs and they just get burned. And these will also burn if I don't connect them properly. Like if I connected the ground with the 5-volt, this may or may not work. I connected the ground with the 5-volt, the power supply, and the 5-volt with the ground. I think this is going to give me an error. If you have any confusion, you see, this device broke because of supply voltage is minus 5 volt, while permitted range is between minus 500 to 7 volt. Voltage pin and blah blah blah. You see how this creates a problem?
When you change that.
Yes, like I totally inverted these. Like don't do this. It's not permitted. That was just totally an inverted connection. So why the ICs burn? There might be 2 reasons. We're not giving the right amount of current, and maybe we're not giving the right amount of voltage. So do you have any more questions?
No.
Okay.
I understood it now. Just send me the recorded video.
Okay, I will also try to send you the recorded video too. So I think I can end this meeting right now. Should I end it?
Yeah, thank you so much.
You're most welcome.
Thank you so much.
Welcome. You're most welcome. Okay, so bye-bye everyone. I'm gonna end this meeting right now.
Okay, bye.
Allah Hafiz.